welcome to the power system protection course. We will continue with a new module on travelling wave based protection. In this lecture, we will discuss on basics on the travelling wave, where we will address on theory of travelling waves, Bewley's lattice diagram, how modal transformation is being carried out for this purpose, and then how the travelling wave being extracted and some of the features which we think will be resourceful in protection perspective. Now, we have seen so many principles in earlier presentations, lectures based on fundamental component, phasor value, allied things on sequence components. So, we have mentioned that most of the available relays are based on sequence components, that is fundamental component or the phasor concepts. That is 50 or 60 hertz component. Now, however, the voltage and current signals available in power system, they contain many more other frequency components which may be informative. So, this is what the other aspects, the travelling wave phenomena and the allied thing in the system during the disturbances, fault, and from there you can say that how the corresponding travelling wave concept can be applied to protection. This is for this chapter. This is not new, this is last so many decades the concept has emerged, but with newer technology both on computer perspective and on the communication perspective, such a technology is on highlight today. Whenever a fault happens to be there, the travelling wave that propagates from the fault point to the line terminals, and this happens almost at the speed of light. The travelling waves are that is why faster, and that is the reason they are the earliest possible information that on the fault that reaches to the relay location. Relay therefore, using such information can have the high speed performance, fastest fault detection can be achieved in using such information. Such waves are now already in use in industry, power industry for long transmission line for fault location perspective mainly. However, the travelling wave phenomena is a high frequency signal, and that is why the associated sampling is much higher than what we discuss in case of phasor based techniques, and that is the major difference between conventional relay and relay or fault locators which we talk about using travelling wave approach. Let us go to the what is the travelling wave which is associated during fault. So, any electrical disturbance like lightning, load change or switching or including fault, there originates a travelling wave because of the sudden change in voltage and associated current. So, this step change kind of thing current and associated and the related voltage leads to waves generated from there and which propagates both the ways in the system. Now, let us consider a distributed model of the transmission system, where we have a small elementary length delta x. This is a distributed model of the transmission system, which we know in the transmission paper. Now, this if delta x has certain value of resistance and then certain inductance and also the capacitance and conductance. and then you can say that we have this corresponding I at location x at a time t, and at the same instant of time we have I x at the x plus delta x distance, and so also the associated voltage V x plus delta x at the same time t. So, therefore, for this you can say that elementary small network, small portion of the network, we can write this voltage minus this voltage equals to this drop. So, that is you can say that the voltage of left side minus voltage of right side is the drop in the elementary section. So, this we have associated resistance into current and L delta x into del I upon del t. Now, the current you can say that here I at x and I at x plus delta x, that equals to the relation based on conductance and capacitance. So, these are the basic equation for this network voltage and current relations. Now, using that relation and considering a lossless line for simplification, and when delta x tends to 0, we can get the derivative form of these two relations for voltage and current based on del V upon del x, that equals to minus L del I upon del t, and del I upon del x equals to minus C del V upon del t. Double derivative of that, these two equations leads to del square B del x square, that equals to minus L del square I del x del t. So, this leads to del square I del x del t, that is equals to minus C del square B del t square, you see here. So, this is intentionally done. So, from this you can say that we can write down that these two are related now, we see here. So, therefore, you can see this you can write down del square B del x del square B del x square, that equals to substitute this one. So, that becomes equal to L C del square B del x del square B del t square. So, here if we see both are voltage relation. So, one is derivatives with respect to x, the other is time. So, therefore, we say you can say that this also we can write you can say that in terms of the corresponding del square I del x t upon del x square equals to L C del square I del x t del t square. So, both voltage and current relations we can write down, and that is we call wave equations, very common equation, wave equation, travelling wave equation, and so. The solution of the wave equations include both can be there well known forward voltage and backward voltage waves and the associated current waves. So, this forward wave, this capital F x minus gamma t, where gamma is the 1 by root over L C propagation velocity, and the backward you can say that wave f small f x plus gamma t, and so this you see here the only the sign change for f x minus gamma t and x plus gamma t. So, this forward wave you can say that goes along the line, and this you can say that the reverse side, the backward side of this one, that is why x plus and x minus. So, V x t is being expressed in terms of this forward wave and the backward wave, capital F x minus gamma t plus f x plus gamma t, forward wave plus the backward wave, summation of these two. Similarly, current you can say that is obtained from there. So, this f x plus gamma t 1 by Z c minus f x plus gamma t. So, voltage and currents are related in that sense, and with the Z c, where Z c is called the characteristic impedance of the line or the surge impedance of the line, in terms of that root over of L by C. V considered expressed as the summation or composite of the forward wave and the backward wave, and so also the current you consider summation of both forward wave and backward wave. And the forward wave can be obtained from the two equations as we see. So, 2 Z c f x minus gamma t equals to V x t plus Z c I, and similarly the backward wave f x t plus can be considered in terms of 2 Z c f x gamma t V minus g. So, what we like to say here at a given location like V x x t and I x t. If we have, we can say that measurements of voltage and currents. So, we can find the forward wave and also we can find the backward wave. So, this is what from this. So, these are available, and if we know the Z c of that characteristic impedance of the line, then we can obtain the corresponding forward wave and backward wave, which you can use for different purposes also. Now, let us go to the more on the theory of travelling waves. So, we see such a system. So, whenever a fault happens to be there, the travelling wave goes here, it goes there, and now suppose you can say that at this point it finds, you can say that a characteristic impedance of Z c, and this side another, you can say that maybe cable, overhead line, and so Z t and so. So, when it meets, you can say that such a situation, then because of this the associated impedance, characteristic impedance different. So, the corresponding currents and voltage get reflected and something is transmitted. So, that you can say that it's the associated, you can say that point at the bus where it finds a mismatch in the characteristic impedance. So, typically we mention here the incident wave and the reflected wave and the transmitted wave. So, the current, you can say that as you have seen in the earlier forward backward, you can say that wave or the reverse wave. So, that this reflected, you can say that wave is having a negative sign in terms of that, and then that relation for current I incident plus this one reflected, that equals to the I transmitted. And then in this case also, for the voltage case, we have the corresponding incident plus the reflected, that equals to transmitted. So, that is being maintained, you can say, in terms of that. So, that leads to, you can say that our conclusion that the transmitted wave can be obtained from the incident and the reflected one. And in all the cases, V I upon I I equals to, and V I upon whatever the in the medium associated medium. So, that equals to consider Z c in this case, and Z t the transmitted side. So, that consider the corresponding Z t will consider will be transmitted one. So, when a travelling wave from a fault point reaches the terminus, the travelling waves are reflected and transmitted from the impedance discontinuity points, that is at the mismatch point. The reflected and reflection coefficients are, the reflection coefficient rho t equals to Z t minus Z c upon Z t plus Z c, and the transmission coefficient is, you can say that 1 plus rho based on this relation equals to 2 Z t considered Z t plus Z c, where Z t and Z c are considered the corresponding medium through which being transmitted, and Z c the characteristic impedance of the medium where it is being incident or reflected back. So, this reflection coefficient, you can say that is reflection coefficient and the corresponding transmission coefficient are being used for, you can say that different analysis. From a given incident wave, we can find the corresponding transmitted and reflected wave at any, you can say that discontinuity or mismatch. So, there are few special cases, there are several, but here you can say that for our clarity we will see here. Let us, you can say that at a load impedance or a termination happens to be matching with the same as the corresponding impedance of the line. So, this you can say that load or the termination is having the same, you can say that L upon C, and ratio you can say that, and that is why this is matching. In that case, the rho, the reflection coefficient, that becomes 0. It means that nothing will be reflected, nothing will be reflected. Now, the corresponding transmission T becomes equals to 1. If you substitute this relation, T becomes equals to 1, and then you can say that the, in that case you can say that the corresponding thing becomes 1. So, everything will be transmitted to this one. So, there will be, it will not find any discontinuity or mismatch at this point. Now, let us consider the short circuited things. So, the corresponding rho becomes equals to transmitted minus this Z c. So, 0 minus Z c, 0 plus Z c. So, that becomes equals to minus 1, and T becomes equals to 1 plus rho, you can say that becomes equals to 0. So, this shows that you can say that the rho that whatever has come, it will be totally reflected back, and therefore, you can say nothing will be transmitted to this one. So, the corresponding voltage becomes equals to this plus this becomes equals to 0, okay. And then similarly, you can calculate for the current perspective also. When it is open, so then you can say that the rho becomes equals to 1. So, whatever is being incident, that will be totally reflected one, and nothing will be transmitted, and that is what we say the perspective of in that sense you can say that 2 the 1. So, this 1 t equals to 1 plus rho. So, that you can say that t becomes equals to in this case becomes equals to 0. T becomes equals to 1 in this case. Now, let us see how this Bewley's lattice diagram happens to be there. That will clarify, or you can say that reflections and reflection perspective. So, let us say here you can say a source having an impedance of Z s, and then a voltage incident is injected at this point, and you have a characteristic impedance Z c of the line, and it is a terminal impedance of Z t, the characteristic impedance of this termination. So, we have reflection coefficient that at you can say that the 0 distance where we are measuring observation point hour, and that equals to you can say that your Z s minus Z c and Z s plus Z c for this side, and at the you can say that reflection from coefficient at this point, which will be incident will be coming to here, and it finds a mismatch. So, therefore, you can say that will be Z t minus Z c upon Z t plus Z c, and then you can say that let us say this voltage which is being injected at this point, either switching or whatever happens to be there for this source also. So, it travels you can say that, and that V f, and then you can say that at this point you can say that something is transmitted to this side and something is reflected. So, we are talking about the reflected, that reflected will be rho V f, which rho at this point. So, that is what we are talking about, the rho L V f, the reflection coefficients at L into V f. So, this comes to here, and then you can say that at this point this again reflected back, you can say that here, but the reflection coefficient at rho 0 is this Z s minus Z c, that is this side source side, and this Z s minus Z c upon Z s plus Z c, and then you can say that based on that rho 0 into rho L into V f, you can say that is the voltage it goes this, and further you can say that with rho L multiplied, you can say that it goes, you can say that comes towards this one, something will be transmitted. So, this side you can say that to the Z t side we are not seeing. So, what you see that our observation at this point, where at this point. So, these are the you can say that corresponding waves arrival time, and you can say that we can notice here. So, this will you can say that give information that what is the corresponding situation in there, and so point what we say that the travel time here you can say that it becomes downward, it is t dash here this point to this, and then you can say that it goes you can say that the midway, and it goes there and reaches here, and again you can say this. So, in a period of 2 t dash you can say that whatever was being sent from this 0 location, I am say that come back to you can say that to the same location once again with a certain magnitude of this one, and the magnitude depends upon the corresponding reflection coefficient of the other end. So, this lattice diagram, Bewley's lattice diagram, either you can say said about you can say that on this axis we talk about physical distance in terms of kilometer, meter or so, and then that is space, and then this time you can say that downward you go, the time increases, the reflected wave comes from the other end you can say reaches at this point. So, this helps in you can say that in different analysis of you can say that the travelling wave phenomena, which we like to use in our subsequent applications. Let us see an example. So, we have a step change in voltage of 100 volt, that you can say that is a step change of voltage, and then we have a system like that. This you can say that source has some ideal source, we have considered here R s equals to 0, and this you can say that step change in voltage be injected to the systems, which has a characteristic impedance of a cable, and then you can say that we have you can say terminations with a low resistance R L, you can say that equals to 60 ohm. Now, the question is here, determine the reflection coefficient at the sending end, determine the reflection coefficient at the receiving end. Here draw the associated lattice diagram showing the value of each reflected voltage. So, what you see here that the reflection coefficient at the sending end rho equals to 0, that rho 0 here. So, that equals to you can say that as we have already discussed from at this point R s minus Z c. So, whatever is coming to this end R s minus Z c upon R s plus Z c, and that equals to you can say that minus 40 upon 40, that equals to minus 1, and reflection coefficient at the receiving end that at this point that equals to R L minus Z c, R L upon R L plus Z c. So, that equals to 60 minus 40, 60 plus 40, and that equals to 0.2 only. So, what you say, you consider here that the reflected wave will only coming to consider that 20% only, the rest will be going into the system. So, let us see consider that what will happen to the voltage. So, 100 volt step input was given. So, that will consider that step voltage travelling wave will be going to this, and then you can say that it will be reflected, you can say that with a 0.2 coefficient that we have calculated here, and then with 0.2 means only 20 volt will come, and here you can say that we have a -1 coefficient. So, whatever comes you can say that is a with phase change you can say it goes to this. So, that will be minus 20 volt without any magnitude change, and here is again you can say that I am say that 0.2 can say that multiplication of that. So, that gives to minus 4 volt, and then here you can say that the phase change with -1 4 volt, and like this it continues. Now, what you notice here, if you are observing at this point you can say that. So, initially 100 volt, and then you can say that finally minus 20 volt, and then again minus 4 volt, and so. So, this observation you can say that will reveal that on the reflected wave and all these things, from which information can be traced out. So, at different instant of time you can say that what is the corresponding position of that travelling wave that can be inferred from this Liebowitz lattice diagram. Now, on the perspective of how the corresponding travelling wave which being originated, you can say that during fault or so can be used for different protection applications and so. So, it is not straightforward like that what we did in case of phasor based or sequence component based protection schemes, where we mention about data sampling, acquisition of the data, and then you can say that person to the can say that the one cycle DFT or any other filters to extract the fundamental, and then use it for the different principles. Here the corresponding from the signal contains also 50 hertz as you know, which is having a large component. Upon that there will be superimposed with some high frequency component signal. This high frequency signal has to be extracted, which represents for this travelling wave perspective. So, therefore, you can say that it requires different other techniques and all these things. So, we will try to figure out that. In case of to extract the sequence component from the fundamental or phasor based approach, we go for this transformation. You can say that what is called transformation 1 alpha square, and so you remember where alpha corresponds to e to the j 120 degree angle. Now, here you can say that what is being done, the modal analysis is being widely used for usefulness of the travelling wave for different applications in terms of protection or fault location also. The travelling waves are extracted by decomposing the phase currents into ground and two aerial modes with reference to phase A using Clark transformation. So, we apply you can say that Clark transformation to the ground mode and to aerial modes, I alpha and I beta for the two aerial modes and I naught for the ground mode as you know. So, this you can say that is the transformation matrix for Clark transformation matrix for the phase current I A, I B, I C. So, we got you can say that considering phase A as reference, you can say that 3 components I naught, I alpha, I beta, and this you can say that is for the considering I A. Similarly, you can say that considering I B phase as reference, we will get another you can say that 3 you can say that components of I naught, I alpha, I B, and for C also as considering reference we will be getting another 3 you can say that 3 I naught, I alpha and I B. So, these you can say that 9 you can say that numbers of I naught, I alpha and I B will be useful information for different application scope in for the travelling wave based approach. The ground mode you can say that signal has more attenuation than the aerial mode, because it traverses through it is ground associated, and more losses in the earth. So, that you can say that is a problem. So, that the signal strength decreases significantly with travel, and therefore, that is not suitable for applications. The alpha mode signal is suitable for analysis phase to ground faults, and beta mode signal is for the phase to phase faults. Now, how this can say that the corresponding travelling wave being extracted. So, like to see here. So, here suppose a relay happens to be there and fault happens to be there. So, the wave propagates from this side and goes to this side. So, both voltage and current can be extracted, but we see you can say that current is being more widely used. The reason behind that the CVT associated transient has you can say that challenge. CVT response you can say that as compared to the PT response is not good for high frequency component, but CT response for high frequency component is pretty good. So, therefore, you can say that in high voltage systems where CVT is being used, the voltage signal becomes distorted for the high frequency component, and therefore, travelling wave approach is not suitable there. So, current information is more suitable in that case because of the response of the proper response of the CT. So, current signals, then we got the samples value to the data acquisition process, and as already mentioned, this is high frequency component. So, therefore, we have high sampling rate, typically megahertz or and so. Clark's, whereas you talk about some 3-5 kilohertz, you can say that in case of normal, you can say that phasor based approach and so. The Clark transformation alpha beta 0, and then you can say that from A, phase B, phase C to you can say that different phases to there. The band pass filter for what? To extract the high frequency component, because you have to reject the corresponding fundamental component and so. Our purpose is not the fundamental, purpose is to extract this, you can say that this one, and note that you can say that this portion you can say that which is everything, because the travelling wave propagates in terms of microsecond order into the other end and again get reflected, whereas we are talking about here you can say in terms of the seconds or millisecond, in terms of 1 cycle 20 milliseconds. So, no, that you can say that the corresponding phenomena which is associated with the travelling wave is being this portion, you can say that the small noisy portions, and that you can say that reveals the all the perspective. So, therefore, you can say that our sampling rate requirement is very high, and also you can say that the scope of you can say that fast relay decision also. Now, you can say that after the alpha you can say that I alpha component, you can say that transformation alpha component of current signals, this becomes this, and so then we say you can say that to extract the high frequency component here. So, because after the decomposition to the alpha component with phase A as reference or so. So, the corresponding after the band pass filter, the corresponding signal which obtains you can say it becomes this. So, what it reveals that you can say that you see here this is the current signal. So, then you can say that this is another one and this. So, it means that you can say that there is a reversal in current. So, due to some reflection and so it happens to be there. So, this if you are talking about at any location at this point availability of this one. So, that means that you can say that the distance of separation between this and this nothing but in terms of the microsecond, you can say that reveals the corresponding time, you can say that travel between fall point to the reflected point to the corresponding observation point and so. So, this corresponding the corresponding travelling wave you can say that which is being observed here, you can say that reveals you can say that different information for relay application and so. And one other thing you notice that because the associated you can say that system has a lossy system with resistance and so. So, and therefore, you can say that the corresponding wave also attenuates you can say that in terms of that, and after subsequently you can say that after several reflections it will be diminishing. So, therefore, the initial portion of the you can say that initial you can say that portion in the time axis you can say that is being usual 2, 3 something like that, you can say that the numbers of you can say reflections will be available. Afterwards, you can say that the strength diminishes significantly. So, therefore, the relay may not be able to see those changes or see those you can say that waves or extract those waves faithfully. Now, same you can say that things here you can say that what is being done if you try to correlate you can say that to this travelling wave based approach, a fall happens to be there m and n, and at a distance of this side and L minus this from this side. So, the wave travels from this side and to this side, and then you can say that it get reflected here also at this bus at the observation bus, and get reflected you can say that from this bus also, and from the you can say that fall point again it will be reflected, and will again from the right hand side also reflected. So, if we are taking observations at m bus and n bus, then the corresponding waves will be available, this kind of travelling waves can be extracted, and then if we consider that correlate these corresponding waves from both the sides or at the local level, it can reveal different information for the fault position or so. So, there are different properties of these modes that 0, alpha and beta I consider that we are talking about. So, the zero sequence mode kind of thing is the least appropriate for the travelling application, because it has more attenuation, dispersion, and so alpha beta modes are less, you can say that having less loss, you can say that, as compared to the zero sequence approach. The alpha, I can say that currents are available for all types of fault. They provide a reliable quantity to detect, you can say, travelling waves, but the beta currents, you can say, provide marginally higher signal magnitude for phase to phase fault. So, both can be considered used for better applications into the protection or so. The characteristic impedance, attenuation and dispersions are in general different for the 3 modes. They are different again for the 3 modes. 3 sets of Clark components, as I mentioned, for the with reference A, with reference B and reference C differently can be acquired, and that is why I can say that it is more calculation intensive, and that too so you can say that to require in the this business should be able, I am say that should be completed in the microsecond order or so, because of the fastness of the, you can say that, of the travelling wave perspective. Features of travelling waves, on that perspective you can say that fault generated travelling waves will appear only when a fault occurs. We can discriminate between fault and load change and so, which can precisely pinpoint the occurrence of a fault, or it can be used for the fault detection. Furthermore, fault generated travelling waves contain the information as fault inception time, fault location where it has originated. We said that Bewley's lattice diagram can be correlated to that. So, the travelling time of the wave is indicative of location of the fault. Faulted phase can be identified also, because where we got the with respect to the reference A and all those things, where you got the corresponding significant amount of travelling wave, and so that will be indicative of that. And we can identify, you can see that faulted line also, if the double circuit line or multi circuit system and so. So, different features available, different features or characteristics available from there, you can see that can be useful for different applications. So, overall we say that power system fault analysis, which we have carried out earlier lectures and all these things, protective drilling as well as fault detections are based on lumped models. Our analysis was lump models, sequence component analysis, but in actuality you can say that for proper modeling of the systems, we require, you can say that, the distributed model, and travelling wave is based on the distributed model of the thing. So, therefore, this is more accurate in that perspective. High frequency component, non-fundamental frequency component. So, we have to extend the to get the high frequency travelling wave, we have to extend the this one with a high sampling rate, and the corresponding fundamental component and other components are to be eliminated from there. Feature characteristic of such waves are to be explored for possible applications. So, the information which should be extracted from such waves is different the way we proceeded with the based on the fundamental component or the phasor based component. We will see in the next, you can see that lecture on different applications of travelling waves for protection perspective. Thank you.